Okay, so what is mu? Right. So mu is actually what we call Poisson's ratio. Okay. So what's a Poisson's ratio? All right. Poisson's ratio is basically define the lateral deformation in a piece of material. Okay. Say if we have a piece of a bar, right? You apply a load to it. All right. So when you apply a load, okay, and now you can see, okay, say this load P here. Then this bar going to elongate, right? It's going to move here, right? So then at the same time, you will notice that the cross section, the lateral direction, the cross section will decrease because the sample will maintain about the same dimension. This you can commonly see. I don't know if you cook at home, right? So when you get a piece of dough and you stretch it, the dough will become longer, right? This piece can become longer, but you can see the cross section will getting smaller, right? Because that's dramatic, so you can see it. But for a piece of metal, this may be small, but even small, it's still there. So when you stretch this part, right? So you elongate delta. So we know when you give a load P, right, you're going to generate the stress. That is P over A. And that generates a strain, right? So the strain will equal to basically delta over L, right? So that's in this loading direction. However, in this lateral direction, similarly, right, the area of this dimension, let's say initially you have a length, let's say it's a square, right? So initially you have a size, let's say the cross section is like this. Okay, so the size is A, right? So when you stretch it, the A will decrease to be smaller. So basically it will decrease. Okay, so to a different A value. So then you can actually, same way, you can define the strain in this lateral direction. Let's say we call Y direction. And that basically is the A prime minus A, and then divide by the initial A. So this is the strain in this lateral direction. And because this is getting smaller, A prime is smaller than A, so this will be a negative value, right? So we define the Poisson's ratio as nu equals to epsilon y over epsilon x. Okay, so we put a negative sign here because with this ratio, we want to use a positive number, right? So because we know sigma epsilon y is a negative value, so therefore this gives us a positive value. Okay, so this basically is the definition of Poisson's ratio. All right. So as we know here, actually, just one quick note here. As we know, you get the stress, right? And you can calculate the strain, right? Then stress and strain, they're related. So basically, sigma equals E, that's Young's modulus, we just mentioned, and then times the strain, right? So therefore, the three set equation get everything linked together, right? So if you know the load, you can determine the stress, and then stress, you can determine the strain, right? And strain, you can determine the elongation, or other way, vice versa, right? You can go from the elongation, determine how much stress, and then you can see how much load you're applying there, all right? We'll have some more discussion later on in chapter 2 about this equation, all right? Okay, now our next key question is, how can you, okay, so how to make, right, a structure safe? Okay, and in this case, what we're talking about right now is a bar, right? So when you apply load to a bar, how can you make sure this bar is safe? It won't break it, right? So to make it safe, as we mentioned previously, you can control the load P, or right, you can control the cross-sectional area. Of course, when you increase the area, structure in general will be safe, and then if you actually reduce the load, right, it be safer. Okay, so this two, right, has to be both taken into consideration. Okay, now look at what's the P and A ratio, right? That's actually can affect this thing. So basically, it's the stress. So stress is P over A. So therefore, what actually matters is this ratio, right? So you can control the stress, and that will control the safety of this structure. Right? Now, how can you make the stress safe? Basically, we know when you have a material, like we talked about before. So when you have a material, when you apply the load, the material going to be linearly deformed, and then if the stress beyond this range, then it will be dangerous, right? So to make the structure safe, we can simply by making the stress smaller than the yield stress, all right? Okay, so the sigma y, that's actually mean the yield stress, right? So I'll just put it here again, yield stress, okay. All right. However, right, if in many situations, it's maybe not safe enough just make the stress smaller than the yield stress, right? Because it's so close to the breaking point, right? To the limit, we don't feel comfortable to use it because something happens, the load can go beyond it, right? And then you don't feel safe enough, right? So we're going to next talk about how can you control it really safe. So we will introduce the concept of safety factor. Right?